This is a report on operations. First core removal and second core loading of the Organic Moderated Reactor Experiment, called the OMRE. This reactor experiment, located at the National Reactor Testing Station in Idaho, is an Atomic Energy Commission project conducted by Atomics International. The OMRE is designed for a maximum fuel element temperature of 800 degrees Fahrenheit and organic coolant temperatures of from 500 to 700 degrees Fahrenheit, with a coolant velocity of 12 feet per second. The reactor produces 12,000 kilowatts of heat. 31 fuel elements with a total uranium-235 content of 25.5 kilograms are used to provide operating reactivity. An important function of the OMRE is to test organic coolant behavior under conditions similar to those of large central station power plants. Another major function of this reactor is the testing of prototype fuel elements for full-scale organic moderated and cooled reactors. The OMRE began operating during September 1957. By March 1958, thermal stability predictions on organic fluid were confirmed by a successful 3-week test conducted at reduced power with the bulk coolant temperature at 700 degrees Fahrenheit. A subsequent series of tests demonstrated the degree of radiation stability of the organic coolant. No significant decrease occurred in the overall heat transfer properties of the coolant. Operation of the OMRE during this period proved to be simple. Low activation of the coolant allowed access to the primary coolant system. The use of standard components and piping eliminated long delays for parts in need of repair or replacement. Most of the OMRE shutdown time was scheduled for test program modifications. For example, during one of the shutdowns, the OMRE fuel elements were relocated within the core to allow higher power operation of the reactor. Based on the records of the dimensions of each OMRE fuel element built, hot channel factors had been determined for critical points in all fuel elements. When suitable radial flux plots are obtained, the fuel elements in the core are redistributed. All work of this type is done over the open reactor, with the coolant level approximately 15 feet above the core. There are no permanent fuel handling or reloading facilities for the OMRE. A tractor-mounted crane is used to handle reactor components. To remove irradiated fuel elements from the reactor, 3 casks were constructed. Each cask will transport 1 OMRE fuel element or 1 OMR test element. The casks are also used to transport in-pile corrosion specimen holders. All radiation shielding is designed in conformance with government regulations, and the casks have been approved for interstate shipment of radioactive materials. The casks have supplemental shields. A fuel element with 1,200,000 curies of activity can be transported in a cask if all 3 supplemental shields are attached. This shows the casks being tested at an Atomics International facility in California. Each cask is removed from its cradle trunnion and placed onto an auxiliary shield which is mounted on a pipe stand. When permissible fuel heat generation rates and heat transfer characteristics have been determined, fuel element removal operations are checked. An OMRE fuel element head casting is used in this test. The tool assembly is lowered and contact made with the fuel element head. When the assembly latch is secured to the lifting plug of the fuel element, the tool assembly is withdrawn into the cask. The cask bottom closure plug is then rotated and raised. After satisfactory completion of tests, the fuel casks and auxiliary shielding are shipped to the OMRE facility to remove a fuel element and an in-pile corrosion specimen during a scheduled reactor shutdown in July 1958. A work platform is used on the open reactor to permit placement of the fuel element in the proper position for removal. After removal of the work platform, A tractor-mounted crane lowers the frame and auxiliary shield onto 4 pipe columns around the reactor. Shock-absorbing pieces are attached to the pipe columns. The auxiliary shield is centered by guide pins through holes in the frame and corresponding holes in the reactor flange. The cask is lifted from the cradle assembly and lowered into the auxiliary shielding. The bottom closure plug of the cask is lowered and rotated to open the cask. Using safety lock pins to prevent accidental drop, the tool assembly is lowered into the reactor vessel. When contact is made with the fuel element head, the tool assembly latch is secured to the lifting plug of the fuel element and the element lifted into the cask. After the bottom closure plug is rotated and closed, the cask is lifted from the auxiliary shielding and lowered into the cradle trunnion. Clamps secure the cask in the cradle. The afterglow heat output from the hottest OMRE fuel element is reduced to about 3.6 kilowatts 1 day after reactor shutdown. If the heat generation rate of an element exceeds 0.8 kilowatts, the cask is filled with organic liquid. Thermometers are installed in the cooling water inlet and outlet to check proper cooling of the element. An expansion tank for the organic is connected to the cask, which is in a horizontal position on the trailer. The 2 cooling water systems for the cask, one of them an auxiliary, maintain fuel element temperatures as low as possible for experimental reasons. The cooling systems need not be used with the less active fuel elements. The 2 casks shown here, one containing an OMRE fuel element, the other containing an in-pile corrosion specimen, are transported to a hot cell on a 25-ton low-bed trailer. Hot cell examination of the OMRE fuel element confirmed the satisfactory performance of this element in the reactor. By January 1959, the OMRE had completed 23,000 megawatt hours of successful operation, and the reactivity of the fuel elements in the original core had diminished. A second core loading was initiated to provide higher reactor operating reactivity for continuation of OMRE test programs. The reactor was shut down and removal of irradiated elements in the original core was started. For this operation, all used fuel elements from the first core loading are transferred in casks to a fuel element washing facility adjacent to the reactor. The washing facility consists of 2 independent wash cells embedded into the ground. Lead-filled adapter rings center the fuel casks in a vertical position and allow the safe insertion and removal of the elements from the wash cells. The washing cycle for each fuel element is a solvent wash, a detergent wash, and a water rinse. This washing cycle removes undrained organic material from the used fuel elements. After the elements are washed, they are transported in casks to a water canal at the engineering test reactor for storage. When a cask is partially submerged to a safe shielding depth, the cask bottom closure plug is opened and rotated. The element is lowered by the tool assembly and nested in the canal. The fuel cask is raised and given a water rinse before being returned to the OMRE for continued fuel removal and washing operations. After all used fuel elements are removed, the criticality control rod support structure is placed over the core vessel, and the control rods and other associated components are checked for proper operation prior to proceeding with the second core loading. In April 1959, new fuel elements of the same type used in the initial loading were inserted into the core. Nuclear control is furnished by a modified reactor control rod system and neutron counters. The temperature of the organic moderator coolant is maintained at 250 degrees Fahrenheit during the core assembly. 9 fuel elements are inserted into the core for the first fuel addition. Fuel elements are carried into the reactor housing one at a time. The core position of each element is decided in advance. No more fuel than 1/2 the difference between the estimated critical mass and the fuel already in the core is inserted during any fuel addition. The second fuel addition consists of 6 elements. The third fuel addition is comprised of 3 elements. Each remaining fuel addition consists of 1 element. Subcritical multiplication counts are obtained after each individual fuel addition. As in the initial core loading, critical conditions are achieved with the insertion of the 20th element. Additional elements are inserted for the loading of excess reactivity to about 8% delta K over K. To furnish data for the continuing research and development of the organic reactor concept, thermocoupled fuel elements are installed in the OMRE. 6 of these elements are located in one quadrant of the core. Assuming the core flux to be symmetrical, the temperature profile of the core can thus be inferred. Another advantage of locating the thermocoupled elements in proximity is the clearance of thermocoupled conduits from a large area of the core. This arrangement lessens the possibility of conduits interfering with the handling of OMR test elements. 3 test elements of the type to be used in organic cooled reactor power plants are installed in the OMRE. They are instrumented to measure temperatures and coolant flows during reactor operation and will provide results on the performance of fuel elements being considered for full-scale OMR power plants. After completion of control rod calibrations, low power operating tests are performed and the reactor is brought to power in June 1959 with an inlet coolant temperature of 600 degrees Fahrenheit, a maximum fuel plate surface temperature of 800 degrees Fahrenheit, and a nominal power level of 11 megawatts. This proven and reliable organic moderated reactor experiment is the basis for a continuing extensive effort to develop the organic reactor concept for small and large power plants, nuclear-powered ships, and process heat plants.